After 9. So we just got into last time sort of an introduction to stoichiometry. And stoichiometry really is calculations that are done based on the equation and sort of what you're starting with. And um, you could calculate things like how much product you should produce. You could also calculate, if you know how much product you produce, how much of reactants you started with. You could also calculate, for example, if you know how much of one product you produce, you can figure out how much of the other one you can produce. And stoichiometry is really for basic steps, for basic problems. You always want to start with the balanced equation. And again, if you do not have a balanced equation, then none of it will work properly. Second thing you want to do is typically they will give you some type of information. So whatever info or value you have, you want to convert it to grams usually, and then you want to convert it to moles. And the way we obviously go from grams to moles is our conversion we've used before, which is the molar mass. Remember, the molar mass is grams per mole, comes from the periodic table, and it's used as a conversion factor, basically. And once you have it in moles, then you're going to do the mole to mole relationship. And the mole to mole relationship comes from the balanced equation. And remember that when we do look at a balanced equation, to just make one up here, we could actually use the coefficients from the balanced equation as sort of a conversion factor. And that's really the whole basis of what stoichiometry is using that as a conversion factor. So for example, we could say there are 2 moles of A could react with 4 moles of B. We could also say for every 2 moles of A, we produce 2 moles of C. And again, these are nothing more than just the coefficients from the balanced equation. We could also say for every 2 moles of A, we get 1 mole of D. And we could also do that for our B here. So for every 4 moles of B, we produce 2 moles of C. Every 4 moles of B, we produce 1 mole there of D. And for every 2 moles of C, we would also produce 1 mole of D. So from this one sort of equation, we actually have 6 different sort of relationships that we could get to use in a problem. Remember, each of these basically can produce, and I'll just do this one, each of these can produce 2 conversion factors. We could say 4 moles of B over 2 moles of C are 2 moles of C over 4 moles of B. So in this particular case, we have 6 sort of relationships. We would have available to us like 12 different sort of conversion factors. Obviously, as we talked about last time, you will not use them all. You just use whichever one that you need. So when you do go to the equation for kind of the third step, let's just say we're given information. We had info about moles of A, and we want to know basically D. We would then go to the equation and look at those 2 things, use the coefficients as a conversion factor. And that really is what stoichiometry is. It's just a conversion factor. And instead of looking it up in a table, thank you, you will basically use the actual balanced equation as the place to get your conversion factor from. Now, the fourth step is very commonly done. And if you do obviously the first 3 steps, at this point, you should be in moles of whatever unit you're looking to get to. Then you typically will convert it to some other unit. And like I said, a lot of times we do end up in moles, grams at the end here. So a lot of times we are going backwards from moles back to grams at the end. But you really could go to any unit at the end, whatever it may ask you to do. But very commonly, like I said, we do end up in grams. So once again, molar mass on the back end here of the calculation is also very, very commonly sort of used. So again, we do sort of follow these 4 steps, and these are for basic stoichiometry problems. And if something is done for you, you just kind of go forward in the steps. Obviously, don't go backwards. And it should lead you to hopefully the right answer. Any question on any of those steps there? All right, so I didn't think we did this one. So why don't we start with this one here? Maybe I missed one. Let's see. Yeah, let me start with this one. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of H2 can be formed by the reaction of 5.32 moles of lithium with water? Why don't you give it a go? Let's see what you come up with here. Again, follow the 4 steps. You want to start with a balanced equation. You want to convert to moles. You want to do the mole to mole relationship. And lastly, obviously, whoops, 3, and moles to some other units. All right, so take a few moments there, go through those steps, see what you come up with here. Okay, so let's take a look, see how you're doing. So first off, in this case, we were not given any sort of equation given to us. We are given it in words. So a reminder that you do want to make sure that you first get the proper formulas down before you worry about the balancing part. So lithium metal is just lithium. Reacts with water, which should be H2O, to form, which should be an arrow. Hydrogen gas, remember hydrogen gas, nitrogen, all those guys come as 2, so it's H2. And lithium hydroxide should be LiOH. So again, here I'm not worried about the balancing. I just want to make sure I got all the proper formulas down first. Now I definitely should turn my attention here to the balancing part of it. And we need to do a little bit of balancing here. I believe maybe like a 2 there, a 2 there, and maybe a 2 there, I think. All right, so I think we should be balanced in this case. We got 2 lithiums on each side. We have 4 hydrogens on each side, and we have 2 oxygens on each side. So we are balanced. So that definitely is balanced here. Now, if we look at what was given to us, we want to know how many moles of hydrogen. So we're ultimately looking for how many moles of this guy here we're going to form. And if we started with 5.32 moles of lithium. So step number 2 is to take whatever they gave us and convert it to moles. In this particular case, this is the only actual number they gave us, and it's already in moles, so we don't have to do that. So again, we just go forward, we don't go backwards. The next thing is actually the big stoichiometry move, which is we're going to go to the equation, and we're going to find the 2 things we're interested in. And in this particular case, we're definitely interested in what they gave us, which is the lithium. And the other thing that we're interested in is what we're trying to find, which in this case is the hydrogen. So this is again where we're going to get our conversion factor from, and from the equation here. So step 1 here, step 2 already done. Step 3, we can see that there are 2 moles of lithium for every 1 mole of hydrogen. And what that's going to give you is 2 possible conversion factors to use. And once again, that is nothing more than the coefficients from the balanced equation, which is why having a balanced equation is quite important in this step or process. Otherwise, your calculation definitely will be off. So these are the 2 possible conversion factors you could get: 2 moles of lithium over 1 mole of hydrogen, or 1 mole of hydrogen over 2 moles of lithium. So now taking our number there, 5.32 moles of lithium, we're going to just do a dimensional analysis. Opposites cancel. So lithium's up on top, so we want it in the opposite location. So that makes our decision of conversion factors pretty easy. Should be the one on the right there. Will give us 1 mole of hydrogen over 2 moles of lithium. And just like any normal sort of dimensional analysis, we're going to multiply the top, divide the bottom, and that's going to get us basically here 5.32 divided by 2 is 2.66 moles of hydrogen. In this particular problem, we are actually done because that is what we're looking for. We're looking for the moles of hydrogen in this case. We actually don't have to do the fourth step in this case. If we were looking for grams, we would need to do the fourth step, and we would need to use the molar mass of H2 to do that, to convert those moles of H2 into grams of H2. This, by the way, is what is sometimes referred to as a theoretical yield, and that is how much of our product we should get out. That number represents the amount of moles of our product that we should get out if we started with our 5.32 moles of lithium. Everything went perfect, nothing side reaction, nothing was lost. That's like your maximum number of moles you should get out of your product, which is our theoretical yield, which obviously, again, we could convert to grams to know how many grams we would get. Any questions on that one there? All right, let's try another one here. We're going to do actually the same reaction and equation, but in this case, we're going to want to know how many grams of H2 if we started with 81.75 grams of lithium, and lithium is 6.941. Hydrogen is 1.008. I think that might be all you need. So once again, follow those 4 steps, balance the equation, convert to moles, mole to mole relationship, and moles to some other unit. All right, so take a few moments there, see what you come up. Okay, so let's take a look. So again here, we definitely have a stoichiometry problem. We have a balance equation already done from the last time. We are, in this case, starting with 81.75 grams of lithium. And again, we do want to get over here to hydrogen, but we are looking for grams in this case. So we'll start with our 4 steps. So we have the equation as balanced, so that's good to go. In this case, the only piece of information they gave us was 81.75 grams of lithium. And we do need to do the second step here, which is convert to moles. If it wasn't given to you, obviously you would go to the periodic table there and get the molar mass there of lithium. And again, from the periodic table, we can see that it is 6.941 grams per mole. So our second step would be take what they gave us, 81.75 grams of lithium, just do a conversion between grams to moles. So in this case, we do need the grams on the bottom so that they cancel out. And again, we're going to multiply the top, divide by the bottom. And in this case here, we will end up with about 11.778. And again, I'm not going to round too much here because this is definitely not the end of the calculation. You don't necessarily have to get an answer at this point. You can kind of just continue on with the calculation if you like. But I'm just going to kind of do it step by step so we can see the steps. So step number 2 is done. Remember, though, that we're not looking for lithium when it's done. We are looking for hydrogen. So that's going to bring us to the third step, which once again is that mole-to-mole relationship. That is, again, really the stoichiometry. And it happens to be the same one that we used in the previous problem here. Is between these two guys, which is what we're interested in. And as we saw in the previous problem, we could see that for every 2 moles of lithium, that will give me 1 mole of hydrogen out the end. And once again, it is just the coefficients from the balanced equation. That's going to give us our 2 sort of available conversion factors, 2 moles of lithium over 1 mole of hydrogen, or 1 mole of hydrogen over 2 moles of lithium. So since I am starting here with 11.778 moles of lithium, I want to get rid of lithium. Lithium needs to go on the bottom because it's up on top. So once again, here the one on the right will be the one that we would want to use. 1 mole of hydrogen and 2 moles of lithium. And that's the big stoichiometry move. Again, it comes from the balanced equation is where we get that from. And we're going to end up here just dividing that by 2. Going to get us 5.8889 moles of hydrogen in this case. Any questions on that so far? That takes care of the third step. And in this particular problem here, we do need to do the last step because we're not looking for the answer in moles, but we are looking for it in grams. And it is important to remember as well that we are no longer kind of dealing with lithium. We have now converted into hydrogen. So we again would need to go back to the periodic table. We would need to get our molar mass of H2, which should be 2 times 1.008 grams per mole, going to get us a 2.016 grams per mole as our molar mass. And just kind of continuing on right here, using our molar mass we just calculated there for our fourth step, we're going to go put grams up on top. So that will be left with grams when it's all said and done. Here the moles will cancel, and we'll take that and times it by 2 here. I think I did that there. Point. Oops. By 2. There we go. And times 2.016. Gonna get us a 11.87 grams of hydrogen would be produced in this case. This again is what is referred to as a theoretical yield. That would be the theoretical yield in grams. By the way, this would be the theoretical yield in moles. So you could do it really in any unit you want, but they're both yields. Theoretical yields or yields in general should always be a product. That is something that's being formed as a result. So once again, in this reaction, what that means is if you threw in there 81.75 grams of lithium, everything went perfect, you should technically get out maximum amount of hydrogen, 11.87 grams. And again, these are our 4 steps that we did. Question on any of those steps there. Now, as I mentioned before, you don't necessarily have to get an answer after each step. You could have just did this all in, obviously, one calculation and just went from one sort of step there to the next. And that is perfectly fine. And in fact, here they actually prefer that you do it this way. I personally don't care if you want to do it step by step or you want to do it all in one calculation. That's perfectly fine. Again, our grams cancel, our moles of hydrogen cancel, and you end up obviously with the same answer here. Is perfectly fine. If you do get an answer after each step, once again, I would not round too much to the very end. And when you're all said and done, you could clean it up. And based on this, this is the only number we had, which was like 4 significant figures. So our answer probably should add 4 significant figures as well. Any questions on any of that there? Okay. Try a couple more, just make sure. That's what we just did. All right, well, I'm going to try this one here. If 765 grams of C6H12O6 is consumed by the body, how many grams of CO2 would you produce? What is the mass of CO2? So basically the grams. So once again, give you some numbers here. Carbon 12.01, hydrogen 1.008, oxygen 16. I think that's everybody you need. And again, follow the same 4 steps. So balance the equation, convert to moles, mole to mole, and moles, some other unit. All right, so take a few moments, see what you come up with here. Okay, so let's take a look, see how you're progressing. So again, just always sort of follow these four steps, especially with basic stoichiometry problems like this. What makes something sort of a basic stoichiometry problem is, for the most part, you're just given one piece of information. So you're just kind of given one number, basically. And that's how you know it's just sort of a basic sort of problem. We do have an equation. I do see some coefficients, so it does look like it is balanced. So that's all good. So next thing. They did give us 765 grams of this guy here, and we ultimately want to get over to grams of CO2. So step number two, we do need to convert into moles. And again, in order to do that, we will have to go to the periodic table here and get the molar mass. And that is of C6H12O6. So just adding up all the parts. So we got 6 times 12.01 for our carbon, 12 times 1.008 for our hydrogens, and 6 times 16 for our oxygens. And that's going to give us about 180 something, I think. 180.2, we will call it. And again, we're going to use this as really just a conversion factor to go from grams to moles. And the real purpose of doing that is for the next step. We do are you going to in moles, everything cancels out. So we'll take the number that they gave us, 765 grams of C6H12O6. We'll use our molar mass. Again, grams need to go on the bottom so that they cancel. Moles will go up on top. And again, like I said before, you don't necessarily have to get an answer at this point, but if you did, try not to round too much. So I will get an answer just so we can kind of see each of those steps. And in this case, 4.2453, I'll take it to a few digits. C6H12O6. Again, the purpose of this is really for the third step, and the third step here is the stoichiometry step. At this point, we're kind of sitting with C6H12O6, but we want to get to CO2. So we're going to go to our equation, find those two things, and that's going to really give us our conversion factor to go from one to the next. And again, this conversion factor is just the coefficients from the balanced equation. So looking at the equation, I can see 1 mole of C6H12O6 will give me 6 moles of CO2. Once again, that kind of opens up to you two conversion factors you could use. You could use this over the 6 moles of CO2, or you can flip it around and put the 6 moles of CO2 up on top and the 1 mole of the C6H12O6. So taking our number from above, 4.2453 moles of C6H12O6. Once again, opposite's going to cancel, so we want the one where it's on the bottom. And that's going to give us 6 moles of CO2 up on top and 1 mole of C6H12O6 on the bottom. Again, those are going to cancel. And we're going to multiply basically our number by 6 here. Again, multiplying the top, dividing the bottom. And that's going to give us 25.4717 moles of CO2. Any questions so far? Again, if we wanted the answer in moles, we'd actually be done. We could just put a box on it, maybe clean up some sig figs there. But in this case, we do want grams, so we do need to do the fourth step, which is take those moles into grams. Once again, though, we have now converted it to CO2, so we will have to go back to the periodic table and get the proper molar mass to use, which is CO2, and that would be 12.01 grams per mole plus 2 times 16 grams per mole. That's going to give us something like 4401 grams per mole. So taking our number there, put a line there, we got 25.4717 moles of CO2. This case, we want moles on the bottom. So a mole of CO2 from the periodic table, 4401 grams. And if we do that there, it's going to give us about 1,121 grams of CO2, which, and now we can kind of clean up some sig figs since this was the only number given to us, which is three significant figures. Maybe something like 1120 grams of CO2 would be good. And again, this here, and actually this here as well, those would be the theoretical yield, one in moles, and obviously one in grams. So again here, if we were to throw in there 765 grams of C6H12O6, we should get off, everything went perfect, 1,120 grams of CO. Once again, the same four steps, and just like we talked about at the end last time, if you did not want to get an answer, you obviously could just go from there to here to here, and just do it all one calculation if you want. Yeah. Any questions all about there? Now, also a really important reminder in terms of stoichiometry, although these few examples that we've done, we've gone from kind of reactants to products. You definitely don't have to cross the arrow. So again, you could do some relationships from reactants to products like we did. We could go from products to reactants. We could also do the relationship between the two reactants. And we could also do this type of calculation between two products. So you don't always have to cross the arrow to do this calculation. You could follow the same four steps and do it with anybody in the equation, whether they're on the same side of the arrow or opposite sides of the arrow, it will all work the same. So again, if I was interested in H2O, I could actually take my moles of CO2 and just figure out how much H2O I would produce. And same thing here, if I was interested in O2, I could take my moles of C6H12O6 and figure that out as well. Or you could even use your H2O moles or your CO2 moles. So you could do these relationships with anybody in the balance equation. Any question on that there? Okay, so these are sort of, like I said, kind of basic stoichiometry problems. And we're going to talk about a little bit different types of problems now. I think we're going to skip this one. It's kind of the same deal. So if you want to practice, you can try that one. We're going to talk about another sort of topic here that is involving stoichiometry, and that is what is known as limiting reagents. And they're sometimes called limiting reactants. And limiting reagents or limiting reactants is the idea that there will always be one of the reactants or reagents that gets used up first. So there is something that is known as the limiting reagent or reactant, and that gets used up first in the chemical reaction. And then there's something known as the excess reagent, and that is you have plenty of. So the excess reagent you have plenty of to do the reaction, and you'll actually have some left over when the reaction is all done. The limiting reagent, you shouldn't really have anything left over. It should all get kind of used up. So the question is, why is this important? Well, let's just think about just a basic reaction. We're going to take A plus B, and we're going to make A and B. And let's just say in this case that the A was the limiting reagent and the B was the excess reagent, right? So what's going to happen in this reaction is because A is the limiting reagent, at some point you are going to run out of A and you'll no longer have A. Now, when I run out of A, is there any way I can make any more product here? The answer is no, right? Because in order to make our product, I need an A and a B coming together. So once I run out of A, there's no possible way for you to make any more products in this case. And the importance of that is it is always the limiting reagent that determines how much product you make. So when we have a limiting reagent sort of situation, there are a couple of things that you have to do. You do have to at some point do a calculation to let you know which one's your limiting reagent. And that's important because that will then allow you to know really how much product you can make because it's all going to be based on the limiting reagent. We actually don't need to do this in a sort of basic stoichiometry problems like the ones we just did because we kind of are only given one piece of information and we could assume if that is a reactant that that guy is the limiting reagent. So we kind of make that assumption on a basic problem. So like I mentioned before, the limiting reagent is the reactant that gets used up first in the chemical reaction. The importance of that again is it is the one that definitely determines how much product you're going to make. So when you're trying to figure out and do a calculation to figure out how much product you would produce in this reaction, you should always start the calculation with the limiting reagent, never the excess reagent, because it is, again, the limiting reagent which determines how much product you make. Now, the excess reagent, like I said, is the one you have plenty of. And also a very common question sometimes is how much of that do you have left over at the end of the reaction? And that is something that you could calculate as well. You could figure out how much you need to use up all of the limiting reagent. You can also figure out how much is still there when the reaction is done. So if we look at sort of an example here, and we want to make workout buddies here, and we got one guy, one girl, and obviously, as we put them together in pairs, we would need one and one, one and one, one and one. And at this point, we have no more on the right-hand side here. So we could only make really 3 completed products in this case. And it's all based on, obviously, here our limiting reagent. Over here would be our excess reagent in this particular case. We could also figure out, like I said, which is a very common sort of question, how much of our excess reagent we have left over. In this example, we have 1 and 2 left over. So we would have 2 of our excess reagents left over as well. So these are the very typical type of questions that you are sometimes asked. So let's just say, for example, we had an equation such as this, and let's just say that we are going to be starting with 1 mole of sulfur, and we're going to react it with 3 moles of fluorine. So let's get rid of that maybe here. So in this particular case, this is our starting amounts. And there are a few different ways that you could do these type of problems, but really the first thing that you want to look at when you have a stoichiometry problem is it a limiting reagent problem? And the way that you know it is a limiting reagent problem is if you look at the equation and you have enough information to get to the moles of each reactant, then it is a limiting reagent problem. So if you see you have enough moles to get to both reactants, so if you have enough info to calculate moles of each reactant, then you know this is a limiting reagent problem. So that is the major thing that you are looking for. Now, in this particular case, they just straight up gave us starting moles of each of these, right? So we definitely have moles of each reactant. So I know this is a limiting reagent problem. And once again, if you think about the previous examples we did not have enough information to get the moles of each reactant. So they're just basic stoichiometry problems. Here, definitely do. So that is the key thing to look for. They will not tell you in problems, hey, this is a limiting reagent problem or anything like that. You have to be able to look at it and go, okay, I could get the moles of this reagent and this guy. Then I know that this is definitely a limiting reagent problem. So how can we solve these? Like I said, there are multiple ways you could do it. Uh, so let's talk about one way here, which is really based off of kind of the stoichiometry calculations we've been doing. So if you follow those same 4 steps of we want a balanced equation, we want to convert to moles, Right around here, you will do a calculation to figure out the limiting reagent. Then you could continue on with the same 4 steps, which is do the mole to mole relationship with the limiting reagent. So you always want to make sure you're using the limiting reagent. And lastly, you could do those moles to some other unit. So it's really kind of the same 4 steps, and we will have to do a calculation kind of in the middle of it. A very, very common misconception people have about limiting reagents and how to figure out which one's the limiting reagent is they will convert to moles like we kind of have here, and they will look at it and go, okay, that's a smaller number of moles, so that's the limiting reagent. And that is not always the case. You do have to actually do a calculation to determine which one's the limiting reagent. You cannot just look at the moles of each and know which one is by the smaller number. So you should not just look at it and go, oh, that's a smaller number, that's going to be the limiting reagent. Doesn't necessarily mean it won't be, but you actually have to verify it through some type of calculation. All right, so no matter what method you choose to use, they're all pretty much the same to begin with. Balance the equation, convert to moles, which obviously we have done here. So now that I've done that, now that I know I have moles of each reactant, I definitely know it's a limiting reagent problem. So now I'm going to come right here to this step to figure out which one is my limiting reagent. So when I'm going to figure out which one is my limiting reagent, I basically can choose either reactant. And what you're trying to do is just a very simple calculation to figure out if I want to use up all of one of my reactant, how much of the other one do I need to put in there? So for example here, if I want to use up all of the sulfur, how many moles of fluorine is needed? So I'm just going to do a basic calculation between the two reactants. So I'm going to start with my 1 mole of sulfur, and going to the equation, I can see that for every 1 mole of sulfur, I have 3 moles of fluorine. So we're looking here in this case between the two reactants. So again, from the equation, I see 1 mole of sulfur gives me 3 moles of fluorine. Just like we did before, opposites cancel. So 1 mole of sulfur on the bottom, so they cancel. 3 moles of fluorine here up on top. And we will end up with here. Got that. Hang on 1 sec here. What's it? 4 moles of sulfur, was it? Sorry, 4 moles of sulfur and 20. I felt like those were not the right numbers. Hang on, we're going to use the actual right numbers here. Sorry. So this is 4 moles and 20. That's what we're using. All right. All right, so this is 4 moles of sulfur we're going to start with and 20 moles of fluorine. There we go. All right, so take my calculation here. All right, so we're going to start with 4 moles of sulfur and 20 moles of fluorine. So now I'm going to use the moles of sulfur and our mole to mole relationship. And that's going to give me 12 moles of fluorine here is needed. That looks a little bit better. All right. So in this particular case, I have now figured out that I need 12 moles of fluorine to use up all my starting amount of sulfur. What I want to compare it to is I want to compare it to how many moles of fluorine I'm starting with, which is up here. Now that I got the right number, that's even better. And when I look at those two, I need 12 moles. I am starting with 20 moles. Do I have enough in this case? The answer is yes, because you only need 12. So yes, I have enough. And what that tells you is because you have enough, The fluorine in this reaction is the excess reagent, and by default, the sulfur here would be our limiting reagent. So that little calculation will help us determine which one is the limiting reagent. Any questions on that there? Now, I actually chose sulfur and fluorine, or fluorine, to figure out how much fluorine I would need to use up all my sulfur. You could have, if you wanted to, done the reverse calculation, which is if I want to use up all of my fluorine, how much sulfur is needed. So you could have done the reverse calculation, and in that case, we would start with our moles of fluorine, which is 20. We would use our same relationship but reversed. So 3 moles of fluorine on the bottom, 1 mole of sulfur on top. Our moles of fluorine would cancel, and we would take 20 divided by 3 gets you 6.667 moles of sulfur is needed. Once again here, we would then compare it to how much we started with. So in this calculation, we see we need about 6.6 moles of sulfur. If we look at how much sulfur we're starting with, we're actually starting with only 4 moles of sulfur. So we do not have enough. And it tells us the exact same thing. It tells us that because we do not have enough, the moles of sulfur is our limiting reagent, and the moles of fluorine would be our excess. You only have to figure out one of them. You don't have to do both calculations, but they both will tell you the same thing. Any questions on that there? So now that I know, for example, in this problem, that the sulfur is the limiting reagent, I could use that to figure out how much product I would produce. So it's important, though, that now that I know that this guy here is my limiting reagent, I should then start with the moles of my limiting reagent to start with. So we would then pick up with the third step here, and I would go 4 moles of sulfur, and now I can figure out my product, which is, again, 1 mole of sulfur gives me 1 mole of SF6, and that would tell me that I would produce 4 moles of SF6. That would be my theoretical yield in moles. And if I wanted grams, I could do the molar mass of SF6 and do that fourth step and figure out how many grams that would be, which would be roughly, it's about 146. So times that by 4. So roughly here we would have something like 584 grams of SF6 would be produced in this case. So this method here is you basically choose one of the reactants. Again, you don't have to do both. And you basically do a calculation between the two reactants where you figure out if you want to use up the first reactant, how much of this second one you need to put in there. And if you do compare and you have enough, then that will be the excess reagent. If you do not have enough, it will be the limiting reagent. Any questions on those steps there? Now, like I said before, sometimes you will be asked how much of that excess reagent is left over. So for example, here we know, based on our calculation here, that the F2 is our excess reagent. And we can know from that calculation, we can then figure out that we have started with 20 moles of our F2. That's what we started with. And we know that we calculated we needed 12 moles to use up our limiting reagent. That will leave us with about 8 moles of F2 left over. And once again, just like anything else, if you want to know how many grams that would be, You could use the molar mass of F2, which is about 38 grams per mole from the periodic table. And that would tell you you had about 304 grams of it left over. Go here, left over. So, like I said, that's a very sort of common question that is sometimes asked. In addition to how much product you would make, sometimes you are asked how much of that excess reagent would be left over. First off, any questions on that there? So, this is one method to do limiting reagent problems. There are multiple ones, so I'm just going to talk about and show you one more method, which is nowadays very commonly sort of taught to people, and that is when you determine it is a limiting reagent problem, you basically do two separate calculations. So let's just use this one for an example here. Maybe we'll borrow that again. What we got there? S and 3F2. So we got S plus 3F2 giving us our SF6. And in this case, we started with 4 moles of this guy and 20 moles of this guy. All right, so here is sort of method 2, if you will. And method 2 is, again, you still really follow the same 2 steps or 4 steps, really. You still are going to balance your equation. You're still going to convert to moles. You're still going to do the mole to mole relationship, and you're still going to go moles to some other unit. Now, the difference in this method is, and really any method, these first two are always the same. So in this case, we kind of already done our first 2 steps here. Now, in this method, what you do is actually just 2 separate calculations. So the first calculation would be you take your starting amount of sulfur and you figure out how many grams does it make of our product. So that would be your first calculation. And then what you would do is your second calculation, which would be go to the other reactant and basically figure out how many grams of SF6 you would produce. That would be your second calculation. So if we did our first calculation here, starting with our first moles, we would take our 4 moles of sulfur. We would do the mole-to-mole relationship between sulfur and the product. 1 mole of sulfur is 1 mole of SF6. Those guys are going to cancel. I'm in moles of SF6. I then could use the molar mass of SF6, which I calculated on the previous page. And that is what there, 6 times 19. It's 146.1 grams per mole here of SF6. Again, these are going to cancel. And here we would end up with 4 times that, basically about 584 grams of FF6 would be produced. So that would be the first calculation you do, just a basic 4 steps from the first reactant to the product and figure out how many grams it would produce. Then you would go back and do your second calculation, starting with your other reactant, and do basically the same thing. So we would start with our 20 moles of F2. We would do our mole-to-mole relationship between F2 and SF6, and that is 3 moles of F2, 1 mole of SF6. These will cancel. Once again, using the molar mass here, 146.1 grams per mole. These guys will cancel. And that's going to get me here 20 times 146.1 divided by 3. We will end up with 974 grams of SF6 would be produced if we started with fluorine as our starting one. First off, any questions on those two calculations? So really in this method, you just basically do two separate calculations, again, using those 4 steps that we did previously. Now, how do you know which one is the limiting reagent? As I mentioned previously, it is the one that is the smallest amount of product produced. So it would be the smallest amount of product produced is your limiting reagent and your theoretical yield. So this is the smallest, and that would mean that this is your limiting reagent, the sulfur that you started with, and this would then be your theoretical yield. You would then basically just ignore this whole calculation that you wasted your time doing, but you did it anyways, but you just ignore it. You won't use it for anything. And as you can see here, you get the same 584 that you get over here in this case. Now, maybe the drawback to this method would be if you were asked, what is the amount of excess reagent left over? You then need to go back and actually do this calculation over here that we did previously. You would have to go back and kind of come back and do this calculation. So, you know, nowadays they kind of teach this method a lot. And if you like it, you could use it. I don't really care which one you use. But once again, if you were asked how much of your excess, you would then have to go back and go, all right, I know this is my excess reagent. You would have to go back and do that separate calculation that we did on the other process to answer that question. So you would have to go back and kind of do that there and see that you know, whatever you had left there. Actually, that's the wrong calculation. You actually just go back and use that calculation there. 4 moles of sulfur and do it this way. 3 moles of fluorine and 1 mole of sulfur. And that get back to our 12 moles of fluorine was needed and kind of go back and finish up the calculation. So one method is kind of like what we're doing in the middle, figure out which one's the limiting reagent. A second method is just do 2 separate calculations, ignore one, whichever one's the smallest is your limiting reagent. You could also, if you wanted to, also compare moles to moles as well. So you don't necessarily have to go all the way to grams. If you want, you can just compare moles to moles. But very commonly, you're asked to calculate the grams. And you know, you can do that way here. So any questions on either of those methods? Like I said before, the way that you do know it is a limiting reagent problem is this part right here. You can get yourself to moles of each reactant. Then you definitely know somewhere along the way you have to do a calculation to determine it. Once again, it is not just the smallest number of moles is your limiting reagent. So you got to make sure you do